Hello and welcome on board. This is Design the Engineering Process, a channel where we give a walkthrough on process engineering operations and design. So, ladies and gentlemen, for those of you who have been following us down this far, you might be able to tell that today's audio quality sounds better than what we've been serving you. And the reason for that is that we had a lot of mentors before starting today's content. I'm just kidding. So, we were able to invest in a better audio system, and we want to use this medium before we dive in to appreciate you and also apologize for you having to put up with our poor audio quality. And from this point onwards, we hope to be able to serve you better in the most way we can. Thank you very much for your support and patience with us. Now, let's dive in. Engineers in the rough, we have a design mission on hand. Your mission, should you choose to accept it, is to simulate the production of hydrogen-rich syngas, aka synthesis gas, using the Autothermal Reforming process, ATR. Take note of that. The process shall utilize methane, steam, oxygen as feedstocks. The objective is to demonstrate how partial oxidation supplies the heat required for steam reforming within a single reactor. Now, a heads up, today's content is going to be involving a lot of discussion. So we're going to be doing a lot of listening as much as we're going to be doing thinking and modeling. Before we move on, we should put this out here that today's content is also custom made for a very kind viewer of ours who watched our SMR content and requested for this, and it's custom made. Hope it serves the purpose. And this is to also encourage you that if you have custom questions like this, help you need, you could put it on the comment section and we will gladly go through it and check the feasibility of, shooting a content on it if it's something that can be done using Aspen Hysys. Now, let's start our discussions. What's the difference between SMR and ATR? That's the first question. SMR, as we covered in our previous content, is a process through which we use steam methane reforming process to generate hydrogen-rich syngas. But do take note the differentiating factor for the SMR, our conventional traditional SMR, we require an external source, a continuous external source of heating, usually external combustion source of heating, supply continuous amount of heat to carry out that, to provide that heat needed to carry out the SMR reaction, which ultimately produces our hydrogen-rich syngas. For our previous content, we did some heating. For those of you who followed us, we did some heating using a heater. Well, it wasn't just some heating, it was quite energy intensive. But you could tell that we did some preheating before going into our SMR reactor. The reason for that is to produce the energy required. So unfortunately, we did not exclusively mention that that type of heater is a furnace, or best known as a fired heater. Not just any type of heater, it's a fired heater, needing fuel for combustion, blah blah blah. No, the downside to that is that for the SMR, the conventional traditional SMR, that external heating process is quite energy intensive, number one. It requires a very high steam to carbon ratio. In our previous content, we used 3:1 steam to carbon ratio. It involves a lot of heat losses, there are a lot of heat losses, and then it requires a lot of maintenance and process safety protocols to manage that process. So that's coupling all these factors together, it doesn't really make it, the best option, your go-to when trying to produce large scale hydrogen-rich syngas. So engineers thought of a better way to handle that process for larger scale hydrogen production, and the ATR came to be. Now, the ATR, Autothermal Reforming process, as we know it, is a process where we still carry out steam methane reforming to produce hydrogen-rich steam gas, but without the external continuous source of heating, which is from our furnace. In the ATR, we do not use a furnace. Rather, we generate our own heat needed to drive the SMR internally using a process or a reaction called partial oxidation, and we're going to look at what that is all about, the partial oxidation. So for now, we can go through our conditions required for the design mission. Feed composition, number one. Methane, we're going to be having 3 independent streams, 100% methane for one of the streams, the other steam 100%, the third stream oxygen 100%. Feed conditions for our methane stream, we're having 30 bar 25 Celsius and a flow rate of 100 kmol per hour. For the steam, we're having 30 bar 350 Celsius without a flow rate being mentioned. Oxygen, 30 bar 25 Celsius without a flow rate being mentioned, but that's where our feed ratio comes into play. Steam to carbon ratio, as we said, the advantages of ATR over SMR is that steam to carbon ratio is lower. Instead of using a 3:1 carbon ratio, we're using 1:1 in this case. So our carbon is our methane, that's a hydrocarbon, 100 kmol per hour, and steam to carbon ratio 1:1 means that for every 1 kilomole per hour of methane, we have 1 kilomole per hour of steam to carbon ratio 1:1 equal footings. So for our steam, it's also 100 kilomole per hour. That's our flow rate for our steam. Now for the oxygen, we have a oxygen to carbon ratio of 0.5. So now that we know that our steam flow rate is 100 kilomole per hour, half of that 0.5, 1/2, the ratio oxygen. So for every 100 kilomole per hour of our carbon, we have 50, basically half of that, 50. So that's our flow rate, 50 kilomole per hour of oxygen. Do take note that this values are for the sole purpose of simple educational simulation, though it's still in line with the real engineering concepts, but it's not. There are other factors that determine what steam to carbon ratio and other parameters you should use for your process. Other factors come into play. We're just using these parameters for the purpose of this content. So the first setup, compress all feed streams from 30 bar to 35 bar. Preheat the methane stream to 600 Celsius, that's some heating. Preheat the steam stream from 350 to 60 Celsius. Do take note, oxygen temperature shall remain below 85 Celsius. Now, do take note, oxygen 25 Celsius initially. So it says it shall remain below 85 Celsius. It means that it could be 25 Celsius, which is our initial condition, and it could be heated to a temperature of 85 Celsius or less. The reason for this control temperature in our oxygen is that, as we know it from our elementary science, oxygen is a huge driving force for combustion. And in an event where you blindly energize oxygen with high energy, it drives your combustion so much with a lot of energy, high energy. It supplies so much energy to the combustion, and in process, we consider safety in the real engineering world. We consider safety control factors, and chances are that you might energize the oxygen too much through excessive heating, and that might lead to a catastrophic event such as fire outbreaks or explosions. So usually oxygen is used at the room temperature. You could slightly heat it up to improve the process. Now, as you might take notes, you can see that we're doing some heating, even though we did mention that the ATR does not require an external source of heating, but that's the keyword there, the external source of heating, the fired heater, continuous firing from a fired heater. It doesn't mean that we cannot do other preheating processes, but what it basically means is that we don't need to do a continuous firing to generate heat energy required to drive an SMR using a furnace. For the ATR, we don't do that. We generate our own heat using partial oxidation. Now, our reactor setup, we're using a conversion reactor pressure, that's our entry pressure 35 bar, reactor pressure drop 2 bar, and our reactions for our partial oxidation reaction, this is what it looks like. And the partial oxidation reaction, the reason why it's our go-to energy source in an ATR is because partial oxidation reaction using methane and oxygen for combustion to generate energy is highly exothermal. So it generates so much heat that it becomes our driving force, and we don't need to do the fired heater energy sourcing, continuous firing to generate heat needed to drive an SMR. We could just simply do it internally inside our reaction to generate that heat needed to drive an SMR reaction. So our conversion base components basically is methane. Single pass conversion rate 30%. 30%. We're going to convert 30% of the total methane to generate the heat needed to drive our SMR. This is our stoichiometric coefficient for the reaction given below. Our conventional SMR reaction. We're still our base component for the second reaction, SMR reaction, is still methane, but do take note the remaining methane after we remove 30% from our total methane given, that's 70% left. So we're using 90% of the 70% left. I hope you're still with me. And this is the stoichiometric coefficient given. Product yield target, syngas product is going to be hydrogen rich, of course, so it's going to be 50% and more, greater than 50% in terms of concentration. Then the second most concentrated component we're expecting in our stream, our syngas stream, is going to be carbon monoxide. And then we're expected to have a methane slip of less than 15%. Basically, methane slip means unreacted methane after the ATR process. And then hydrogen production in terms of flow rate is going to be 150 kilomole per hour, more than 150 kilomole per hour. Now that we have our mission conditions in check, we can head to the modeling and simulation environment. We are currently in the modeling and simulation environment. As always, for those of you who do not know how we got here, you're probably in the right dimension at the wrong time, so do make sure to watch our previous contents. Our fluid package of the day, the very, nope, not Mr. Peng Robinson, his elder brother, PRSV. So, first thing as always, create our streams. We have 3 streams for this operation. So we're going to bring down 3 streams. And let's just shift that back. For the first stream, we're going to call it, let's call it methane. Remember the temperature, it's at 25 Celsius. Initially 30 bar with a flow rate of 100 kilogram mole per hour and a composition of 100% methane, mole fraction 1. Okay. Methane stream successfully created. Next up, we're just going to space this out. Next up, we have our, should we call this steam? Yes, let's say steam. Temperature 350 Celsius. So from the steam generation units, probably our plant, basically our steam is supplied at 350 Celsius and a pressure of 30 bar also, and a molar flow rate of 100 kilogram mole per hour, also 100% steam. Well, would you look at that? We forgot to add, did we? Yes, we forgot to add water as a component, so you could just go back and do that. Much better. And as you can see, it reflects, so mole fraction 1, steam generated. Then we're going to call this our oxygen. And we're going to give this one also. We'll have mole fraction 1, and the temperature is 25 Celsius. Initially also 30 bar, a flow rate of 50. Good. We have our 3 feed streams created, but then remember they are all compressed to a pressure of 35. They're all compressed to a pressure of 35 bar. The reason why we're compressing, of course, they are gas. You don't pump gas, you compress gas. But of course, you know that. So, a compressor, 3 actually. Good. Methane, we're going to call this ecomp1 because you need an energy label, but you know that, of course. Compressed methane. We just need to increase 5 bar. So change in pressure is just going to be positive 5, which gives us 35 bar. Good, and it raises our temperature, which works in our favor because of the relationship between gases. Temperature and pressure directly proportional, blah blah blah. But of course, you know that. And then we have our steam also. Inject our steam. Call this compressed steam. Call this ecomp2, and then give it a positive change of 5 bar, which makes it 35 bar, and 379 works in our favor again. Now for our oxygen, this is the tricky part. 25 Celsius. Well, let's see when we compress what it makes of that. For now, let's leave our room temperature, the oxygen. Do take notes. Oxygen is supplied, or maybe in your plant, we're talking engineering, in an engineering scenario, of course, an ASU, air separation unit, where it collects air and separates nitrogen from oxygen and some negligible other components present like argon and blah blah blah. An ASU, so basically take the oxygen. In case you're wondering why you wouldn't just take air, and use for the partial oxidation. The reason it's called partial oxidation is because you use oxygen to do that. In an event where you use air, remember that air is predominantly made up of nitrogen. So, and nitrogen is an inert gas. It doesn't partake in a reaction, but by all means, it will dilute. By all means, it will dilute your syngas, and you will have to separate the nitrogen in the long run. So basically, to avoid the stress and complications in processing, an air separation unit is needed, or you could just get supplied pure hydrogen, pure, not hydrogen, oxygen pure, an oxygen pure stream, basically pure oxygen for the process. So that's the reason we are using pure oxygen. So oxygen, in we go. Ecomp3, call this compressed oxygen. Compressed oxygen. There we go. And we give it a positive change in pressure of 5 bar. And we do look at that, our temperature 42.78 Celsius. Now, the next step is to do the mixing. We could do the mixing, or rather, I think it would be better. Let's do the preheating. We might still need some preheating because we're asked to preheat to 600 Celsius. So we're going to be doing some preheating. Some preheating. Actually, you know what? Let's take a gamble. I love this. Let's try and be engineers and recycle energy, basically. Recover heat. So where are you? There we go. We're going to use a heat exchanger, and we're going to see the reason why. For those of you who followed us in our previous content, the ammonia synthesis content, you saw the reason, and we're going to try and do that here. We don't need that for the oxygen, of course, because we don't need to be above 85 Celsius. We are currently at 42. Let's work with that for the meantime. So we're going to put in our compressed methane through the tube side and call this tube out 1. And we're going to basically leave the shell side empty for the meantime. And we are going to raise our temperature. Magically raise our temperature to 60. We're going to magically raise our temperature to 600 Celsius. And do we need a pressure bar, a pressure drop? Well, yes. Let's say 0.5. So that inherently changes our change in pressure. So please do take notes. We're going to be having a pressure change in our pressure. Where are you? Click. Come on. No. There we go. 5.5 bar instead, to account for the pressure drop of 0.5 bar in our heat exchanger. We're going to do the same thing for our steam. But because oxygen is not going through a heat exchanger, so we're going to let it be 5 bar. Parameters 5.5 bar. Let's see. Good. So there we go. Compressed steam also goes into the tube side, and we're going to call this tube out 2. We're going to leave the shell side empty also. We're going to account for the 0.5 bar pressure drop in the heat exchanger, and we're going to make this 600 Celsius, and we are good to go. So as you can see, 600 Celsius. I got that the other way around. This is supposed to be 30 bar. So it determines, you know what, let's just do that in the parameters. 0.5 bar. Thank you. Tube side 0.5 bar. Let's just do that, and it automates it. Yeah, 30 bar, much better. The same thing for our heat exchanger here. Just take this off. Parameters tube 0.5 bar, 30 bar, 35 bar. Good. So 635 bar, 635 bar, and then as the mission requires, we're going to mix the 3 streams. Compressed oxygen. I think I rushed that, but we're going to fix it. I'm going to call this mixed. Oh, it's let's just go. Now flip. I think I need to properly put that. Delete. So 2 out 1 first, 2, 3. Oh, come on. At the very least, you should walk now. You know what? I'm so obsessed with it. Let's just let it be.